Okay. So of course, this is where the homework is. Homework 2 is due at the end of the week. It's all problems from chapter 1. If you have an older version, let me know. I'm happy to send you the exact text for those versions. And we'll talk about that later. Slides are down here. Lectures are down here. And then we'll talk about peer grading in a second. There's a nice little link in here. You can click that. And we will be doing peer grading. It'll look like this. Okay. And I'll talk about why we're going to do that in 2 seconds. Okay. So let's talk about any questions before we start. I know that there's no questions because we had a help session earlier and I saw almost all of you and none of you came to the help session. So I know you don't have any questions, right? Yes. Oh, that's interesting. How would I find that out? The syllabus. Very good. Why would I say something if I don't want you to understand it? Very good question. Okay. Any other questions? Any other questions? Just read. No, that's all I ask. If you ask a question like, where do I find XYZ? You don't have to have memorized it. In fact, don't even memorize this book, right? The point of learning is not memorization. It's knowing where to look for the information. So if you have a question like, where's the syllabus and where's the syllabus? Where's the answer to that? That's on Canvas. And where's the student help session take place? No. Why do you know that? Because you saw me in there, correct? Okay. And how long are they? 30 minutes, that's correct. Will I stay for the whole hour? No. Of course I will. Don't be silly. I like helping. Yeah, so I will leave if people don't show up. But if you're there and you have a question, you arrive at 29, you're like, oh, I got here just in time and I have 400 questions. I'm like, let's do 399 of them. Okay? So you always have to have a little bit of extra questions. Okay. So what's any other questions before we get started? Okay. Also, we're going to talk about the velocity diffusion. As far as I think a lot of people in their progress reports had issues with the explanation of how shear works in velocity dispersion. Might have seen that. Like, what does viscosity mean? We're going to come back to that when we talk about strains, but we can also talk about that in the student help sessions if you want a better explanation. Because it was clear that most people are like, what the fuck? Don't forget, you need to make a progress report if you haven't done that already, and title it properly. You want to title it progress report so that I know your name is attached to it, not like reflections. Okay. What was the tallest straw? Yeah. 10.2. Okay. Or in human terms? 30 something feet. Oh, okay. Right. Yeah. I who knows what a meter is? So can you do it from space? No. So this is why we can't get astronauts drinking water, right? No, I'm just kidding. That's harder. Okay. And we'll talk, if you want to talk about, especially in the help session, we'll talk about the idea of moments. I think some people had some questions about what moments are when you're talking about integrals, but this is just a fancy way of taking averages. Okay. What's that? That looks like a bullet in water. Like a bullet in water. Interesting. Okay, I like that. It's not correct, but it's interesting. Yeah. Hold on. I can't hear Rolanda.
It reminds me of like a wave on the string, but like one end is fixed.
Okay, so does this look like fluid? Okay, so some people are saying airflow, bullet, wave on a string. Okay, bubbles in water or smoke in the air. So if you tilted your head to the right and I told you it was smoke, would it look like smoke now? Yeah. In fact, it is bubbles, but the same phenomenon is occurring here. So this is a visualization technique where you create little bubbles in the water, cavitation bubbles, then you can track them. The bubbles, really small bubbles, don't pop right away. Okay? All right. We're not going to do that though. I already talked to you about homework 1 being due today. This is a feedback focused class. I want you to understand the material, not worry about, okay, I turned it in and I got my A and I don't give a shit. I'm out, right? Mm-hmm. So you have to give a shit, unfortunately. So I created a little Google form and you're going to peer grade each other's work. This is up to you. You decide you don't want to peer grade, that's fine. You don't want to see what other people turn in, that's fine. You can't avoid me doing this. So if you turn work in, it will go up. And especially when it comes to doing the homework problems, this will be a benefit to you. And why do we think that? Because as you put the homework up, you'll see different ways to solve the problem, right? So you'll see, oh, okay, I could have skipped this step. I didn't have to do that. I didn't have to explain all these parts here. And I will respond directly to every homework that I get, and I'll give you feedback, right? In general, my rubric is something like exceed expectations, satisfactory, or unsatisfactory. Okay. Homework 2 is live, and it's due on Friday. Okay. People are asking me probably, well, Mateo, you never had deadlines before. Why are you going to have deadlines now? Why would I have deadlines? Well, we talked about at the beginning of the semester, it helps to break life down into eatable chunks. You let everything wait for the last week, you will be overwhelmed and you will cry. We don't need more crying. I mean, we're already going to cry, but we don't need more crying, right? Okay, so give it a try. The easiest way to do poorly is to not open the book, is to not even attempt it, right? Ask questions of the material, ask questions of your students, ask questions of me, open up ChatGPT, give it the prompt, see what kind of bullshit it gives up, right? Make sense? It's not very good at answering these questions. Already tried. Okay. So let's go back to what we were talking about. First law of thermodynamics. What was that again? Essentially, it's a statement about, yeah, it's a statement of energy. And on one side you have temperature and work. Heat and work. Okay, heat and work is important. What's the difference between heat and temperature? Heat is a different type of quantity. We tend to think of it as I'm warm, but that's not what it means. What does it mean in physics? Transfer of energy. It's energy transfer. Temperature is what? That's right. It's how much the particles are moving. It's an intrinsic quantity to the material, right? Something that's described by the material itself, not an exterior force. So recall that we talked about heat and work as being extrinsic things to the system, and the internal energy, E, as being intrinsic to the system, right? Okay. We talked about intensive variables and extensive variables. Oh God, that sounds a lot like those other words I just used. So what's the difference between intensive and intrinsic? So of course, the letters that you're looking for here, in means inside. Okay, X means outside. Okay, we can do that. Exoskeleton. I don't know what that would be called, but you know what I mean. Okay. Intensive, right? What are intensive variables?
Yeah. It's just like individual particles of the system and not the whole system. So like kind of like very specific about it.
Right. So they're quantities that are looked at on a per particle basis. So it's divided by the total number of particles, whereas extensive variables describe the entire system. Okay. Intrinsic quantities, a different word, is properties defined by the material. Extrinsic properties are stuff outside the material. Fuck, that's a lot of words. We barely started. Okay, everyone had coffee or whatever it is you take? Okay. So let's talk about state and path. Okay. So heat, work, and energy are all different. Heat and work appear at the boundary of the system. We just talked about that. Whereas the internal energy resides within the fluid itself, right? And here we're going to live in this space just for basically one lecture. We're going to live in PV space where this is pressure and this is volume. And in the pressure volume space, in order to move around, you have to change the energy, right? What is PV approximately proportional to in a ideal gas? Proportional, just proportional. That's equal to, what is proportional to? Temperature. Okay, so I want to know what the feelings are here, right? What are the vibes? Okay. So I have TV here and T on the other side. So these are state variables. There's something that describes the entire state. Right? And this path that you take to move around is going to change. So what do I mean by that? When I go from a point 1 to 2, and then down to 3, and then back up, I'm doing different things. If I go from here to here, what is that process called? Change in volume, change in pressure. It's a simple word. You've heard of it before. Hold on, no. That's a more intense word. This is a normal word. What happened to the volume here? It went from 1 to 2. Volume went up. Expansion. Okay, so this is expansion. Good. And what's this return path? Volume go down, pressure go up. Close? Compression. Okay, expansion, compression, expansion, compression. So you think about this in the context of a balloon. Balloon go up, balloon expand, balloon come down, sometimes balloon compress. Okay. The process of changing the volume of a parcel will require heat or work. It will change the interior state. Okay. Is this clear? Have you seen this before? Okay. Is it elementary school? Elementary, my dear Watson. Okay, so frictionless systems, right? So let's say I go from here to here to here and back to here. Okay, I return to the state 1. And at the whole time, I respect equilibrium. Now, what do we mean by that? We mean that at every single moment, we are exchanging with the bath around us. We talk about it in context of like a heat bath, able to exchange energy with the nearby reservoir. Okay. And if I can go from 1 to 2 to 3 back to 1, that's a reversible process. Because then I could potentially go from 1 to 3 up to 2 and back to 1. Okay. So when we relate them, we do so through something called an equation of state. You don't have to memorize equations of state. You've already memorized one. We've said it already. What's the first equation of state that every student learns?
PV equals NRT.
There you go. PV equals nRT. So this is a relationship between pressure, volume, and temperature. There are other ones. What does this little one say?
Is that talking about PV pressure?
What does little p mean?
That right?
When it's little, it means it's single bar.
Oh, okay. All right. Yeah.
Okay, weird. All right, what's this one? Correct, energy. Ooh. What's this one? Close, but we're not there yet. I wanted it to be salinity, but entropy would have worked here too. So the salinity, for example, how much dissolved salts there are in a liquid will depend on the pressure, the volume, and the temperature. Right? Because if it's hotter gas, you can dissolve more solids in it. Okay. So don't ever memorize these, but know where to find them. And you'll see there's some fun connections when you start putting them all together. What does enthalpy mean? This is the equation, where did I put it? H. What the heck is this? What's an H?
Thermal energy, pressure, volume, temperature.
It's the sum of thermal energy. And you would say that like E. You define it this way. And what? Pressure. Okay. Why would you want that? Yeah, but I have the energy here, right? And then I have what here? Temperature? Well, we could relate it through the temperature, right? We do know that these things are related to the temperature. But according to our equations of state, they're sometimes also related to things like the density. Right? The density, of course, could be related to these other things. The equations of state are not always so uniform. But you're right that we want to measure these types of quantities here and their relationships to temperature, right? These are internal, these are external, right? The fun thing that we can do, you'll just start hitting this with derivatives. How does this thing change? Okay, and it's a math exercise. So it won't make any sense at all. Start doing derivatives on it, you do chain rules on it, and suddenly you come up with these really weird quantities called specific heats. Okay, and you'll have to make some assumptions. You'll say, I'm going to assume a constant volume. I'm going to take a partial derivative. So assume that my volume stays the same. How does this quantity change with changing temperature, for example? Or how does it change with respect to, say, a constant pressure applied to some box, and then I change the temperature? And what you're describing there is you're describing a material property. Okay, the specific heat describes how well does a material exchange heat in all of these different ways. Right? Okay. These are measurable quantities. They're empirically found. Usually. They're weird. And sometimes when they're very, very basic gases, like you have like a hydrogen gas, you can do the quantum mechanics on it. Or if you have like H2, you can derive this for. Diatomic molecules you can derive this for. But you can't just like randomly derive this for air. Okay? You just measure it. Make sense? Let's keep in mind, of course, that a lot of the initial gas thermodynamic stuff is all empirical. So it all starts in the 1800s before they have access to quantum mechanics. Then you derive quantum mechanics and it makes, all these derivations make sense. But you're not going to do that here. That seems awful. Okay. What's the second law of thermodynamics? This is the important one.
That one that's always increasing.
What's always increasing? Yeah, okay. So this is the one that most people are familiar with. It's the definition of entropy. And what would be an example that you would give to, say, your cousin who you're trying to explain this to? Adult cousins, assuming it's not a child. Yeah.
You can't put fork back.
Okay. A different one.
Dropping a teacup on the ground and it'll shatter. It won't.
Oh, okay. Having it shatter, right? That's the important part. Because right, I could do this. That's reversible. Right. So what's the non-reversible part? You didn't see how cool that cup was.
The part where it breaks.
Part where it breaks. So what's non-reversible now?
You can't put all the pieces back together exactly to have it in its original state.
Okay, it's like a Humpty Dumpty situation.
Yeah, there's
Okay.
only one possibility of being.
Okay. So I wouldn't say it exactly like that. It's a perfectly good example, right? The dynamics of the cup breaking, right? You might convince yourself, well, I could calculate that this shard would go there, and this shard would go there, and this shard would go there. And you might be able to get into an argument with someone about chaos, and that would be a wonderful discussion, right? You're right, but it might lead to a discussion. Instead, what you could say is, what if you took a deck of cards? Okay, totally unshuffled, right? All in the correct order. 1, 2, 3, so on and so forth, right? Different colors. And you start shuffling. What are the odds that you get them and they're sort of randomized? Pretty good. You expect that to happen because that's why you shuffled the cards. Okay. What are the odds if you keep doing it, they'll end up back sorted? Nothing. That is the definition of entropy, right? Heading towards disordered states. Okay. Even though the action is repeatable. Shuffle, 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 heads away from the most disordered state, right? Or from the most ordered state. Okay. So that's how we're going to think about it. Because this is giving us basically our idea of an arrow of time, how we look at something like that first picture. We go back. Sorry, I'm going all the way back. You already know intrinsically which direction is the starting location. Yeah, you know it's on the left. Why? What?
It's not messed up.
It's not messed up. Right? As it heads towards the right, if it gets messed up, it stays messed up. It does not collimate, or it tends not to. Of course, we can force it to do that, but we do work when we do. Okay. Okay, so that's the beginning of entropy. When you look at something like how you write this, you have to define a weird new definition. Okay. Something like this. TdS equals delta Q. Okay. And this is for a reversible process. So where's the entropy there? What? No, I'm asking, where is the letter of entropy? S. Cool naming stuff, folks. Okay, entropy, S. Good. All right. And if you combine this with our previous description, you can write something really fun. You can write it like this. Okay. And that's sort of your traditional second law of thermodynamics. Okay. So this is an integratable function. So the changes that happen in temperature are due to changes that happen in energy and PdV. Okay. Let's see, what other things do I want to say here that are really important? Yeah.
So with that equation, it would assume that pressure is constant?
No, pressure can be a function of V,
Oh,
for example. Yeah, so even though this one up here is only for reversible processes, if you follow the math through, this is always true. Cool. Thanks, thermodynamics. If you want to, you can derive that. I think that's example. Oh no, it's not in here. But you can do it yourself. It's pretty straightforward. You just take chain rules. A lot of thermodynamics is chain rules. Okay, and then defining stuff that you don't want to actually have to calculate, like specific heats. Okay. Let's talk about compression really quickly. So in a compressible fluid, isentropic oh shit, what does that mean? Isentropic. Entropy stays constant. So let's break this word apart. What's isa? The same. Okay. Other words that have isa?
Isothermal.
Isothermal.
Isobaric.
Isobaric. Isotropic. Isopod. No, that's different. Okay. Okay, so what if isentropic? So here is the word entropy. Oh, I see it now. Okay, you just cover up the I. I get what that word means. Isentropic, not a magic trick, right? Okay. So isentropic variations in density and pressure propagate at a finite speed in a compressible fluid. So what did I just say? No clue. Okay. In a compressible fluid, what does that mean? You can squish it. You can squish the fluid. Good. Okay. So slight changes in the density are possible. Yeah, that's not always true. So isentropic means what? So the entropy was a measure of what? The disorder in the system. And if we go back one step here, let's go back one more step. Where'd it go? Okay. Frictionless equilibrium respecting changes were called reversible. Reversible changes, do they change the entropy in the system? No, they have to be constant entropy. Because if they're reversible, right, they have to be able to go back and forth. Whereas if the entropy is changing, right, then by definition, there's a direction, right? Non-reversible processes. Okay. So let me ask a different question here. Isentropic variations in density and pressure in a compressible fluid propagate at a finite speed. What am I saying? Yeah.
I have a question. Is what a compressible fluid? I thought fluids were. Example of a compressible fluid.
Yeah. Okay. So you're in one right now. You're hearing me because I'm compressing fluid
Oh.
with my throat.
What is the isentropic variation? Is it saying something stays the same? What's the variation of something that stays the same?
So recall here that you have different things. So on this side, let's imagine that this quantity on the left-hand side is going to change, right? So you could change all of these different knobs. I can change the internal energy, you change the pressure and the volume. So let's say I want to compress the volume. What would happen to V?
Go down.
Go down. What happens to P if I don't want temperature or energy to change?
It has to go.
It has to go up. Oh, so if this thing here is constant, I can just make these two play with each other, right? So in fact, when I think about compressing a fluid, right, you kind of already do this in your head, even though it's not specifically called for, okay? I make a fluid smaller. You assume the pressure goes up. That's not always the case, but it's just with most of what we work with. And if you rarefy a gas, if you expand it, pressure goes down. Does that make sense? So what does this top line say? Yeah.
So are the variations predictable? Is that what you're saying?
Yeah, they're propagating at a finite speed.
Basically, then eventually, stop propagating.
Isentropic doesn't mean that it's dissipating. In fact, isentropic means the opposite. If I create a propagation, it will go. Will not disappear, it will not decay. Yeah.
I was reading, I guess when I'm picking up propagating waves, but is it kind of describing like sound?
Exactly. That's exactly what it's describing. This is the inherent sound speed of the medium. So currently I'm speaking and you're hearing me. There's a delay. You don't notice the delay because we're sort of conditioned to be like this. But if I was very far away, you would see my mouth move first and then my voice would get to you. Right? That is the travel of this pressure wave that's coming up. And put your hand in front of your mouth right now. You will notice, I mean, you're not talking, hopefully, but if you were talking, you would notice that air is coming out of your mouth and hitting your hand. And it hits in different spots. This is how speech language pathologists work, right? They try and fix how the distribution of the air coming out of your face, which is sound. Okay? Comes out at a finite speed. So for a given temperature and pressure, you have sound speed. Okay, what about this thing right here? There's sound speed in the table?
Yeah.
There is, yeah. It propagates through the table at a finite speed. It's different because it's a hard body, right? What about if you're in liquid? In the water. What's that? No, you're in water.
When you.
Is water incompressible? It'd be really bad if water was incompressible.
There's like examples of it, like whales communicating with each other.
Right, whales can communicate. They have whole songs. They're really cute songs about how much they miss each other. You ever heard them?
Yeah.
They're beautiful. And they travel for hundreds of miles, all around the globe, singing to each other. It's beautiful. But it's compressible medium. Okay. Are there a lot of incompressible mediums? No. No, this is a spherical cow that we use to teach students at the beginning. In fact, everything is much harder in life. What would the sound speed be for an incompressible medium?
If you can't compress at all, then no time goes through it because.
Yeah, that's a very good question.
If you can't compress it, you can't.
Okay, let's imagine now. We're going to do a thought experiment. I have a fluid, okay? It's here. You can't see it. I press. It cannot be compressed. And you're over there. When do you feel that?
No, I think it would.
Yeah.
Once it
Yeah, I think it would. No, because that means that they can't. All of it would be pushed. It would be like a wall.
Oh, the.
Exactly.
Oh.
No,
Yeah.
it's instantaneous.
Okay.
Okay?
Oh, it's like.
All right.
So the sound speeds are infinite in an incompressible medium.
Yeah.
Okay. That makes sense? You feeling intuitive about fluids right now? That's okay. We won't deal with a lot of incompressible fluids except for where we have to. We use them as a device, but they're useless. Okay? Okay. Fluids contract and expand. Everyone knows that, right? Metal rod, expand, contracts. Same thing's true of fluids. We're not going to spend a lot of time on that unless you have a question. Questions about this before we go into perfect gases? What's a perfect gas?
It's a perfect answer.
Yeah.
The thing that I get is the gases, but I don't think that's right.
Nope. Those are noble gases.
Yeah.
So the words noble and perfect. Yeah, perfect descriptor, scientist. Good job.
For the density and for the spread out.
Okay. Huh. What do you mean by that?
Like there's no fluctuation in the density in the gas.
Fluctuation in the density. We want some fluctuation in the density. That's what we're gonna use. Yeah. Okay, so I like what you guys are thinking. You're thinking like about what the definition of a perfect gas is. I'm just asking, how would you describe a perfect gas? Yeah.
The one that behaves intuitively.
No.
That
That would be a helpful gas.
The gas with a single element.
I'll give you a hint. I've already written it today. PV equals nRT. Damn it, that's a rule. Oh shit. Okay, so PV equals nRT. Is that correct? Did I write that right? No, I did.
Oh,
What's that?
you change part.
Oh, okay. Interesting. Okay. So we say that wrong a lot, don't we? Is this the better one?
That's a little bit of a pen.
This one is better. Anyone who uses nRT is not my friend. Okay, this is for physicists. Boltzmann constant, good. Okay, why is R less helpful? You're gonna see in a few seconds. Okay, so in fact, R is based on some understanding of some weird things that we just talked about. R is down here. Okay. R is the difference between the specific heat at constant pressure minus the specific heat at constant volume. Why would those possibly be related? They just are. These are empirical relationships. Do not ask that question. You won't like the answer because it involves a lot of math. Okay. But interestingly enough, we get this fun thing, gamma, which is the relationship between the specific heat at constant pressure divided by the specific heat at constant volume. And we can use this. It's very interesting. Okay. So this is the form that everyone likes. It's not the form that we're going to end up using just for these examples here. The other form is maybe I'll do it differently. Be consistent here. Rho. Why is it rho? Yes, that's what rho is, but why is it rho?
It's like the number of total molecules over like.
The volume was here. I brought it over here, and it's N over V. And I have to do a little mathematical mumbo jumbo, right? In that process. Because I want to include stuff like you have a specific gas, for example, you want to take into consideration the mean molecular weight, how many of those items are in a mole, etc. You can work all that out, and you'll go between this constant R and this constant KB. Okay. Okay, hold on a second here. So, okay. These were, I think, the questions that you wanted to say when you're talking about what an ideal gas is on a molecular level. So it's when the attractive forces between the molecules are negligible. And importantly, it's when V over N is much larger than the average volume of a molecule. So you can't do this when you only have a few number of molecules. Your space is like this, and there's only a couple molecules in here. That's not going to work. But this is mostly the case when we think about any sort of idealized fluid that we encounter. So it's not the case for water, but it's certainly the case for what we're breathing right now. The first approximation, ideal gas. Okay. Questions? Let's talk about a couple more words. What's that first word? My goodness. Are you reading or did you know that?
Yeah.
Okay, let's ask this separately. What does it mean?
Coming in or out of this.
Okay. That's the same words. We're going to like grind those gears of knowledge, make sure we disintegrate that knowledge and pour it into our brain hole. Okay. So this is where the word comes from. I thought that was really weird. Impassable. So what's the thing that's impassable in the word adiabatic? Just heat. Heat's the thing that's not passing in the adiabatic system. Little reminder. We did ISA already, but what's that word on the right? Isobaric. What is bar? Pressure. ISO. No change. No change to the pressure. Okay. Isentropic. No change in the entropy. Isothermal. No change in the temperature. Isovolumetric.
Not really.
Yeah.
No change in the volume.
No change in the volume. Isopod.
That's a bug.
It's a bug. That's a bug. Okay. Just making sure you're all still awake. Okay. Okay. So adiabatic processes take place without the addition of heat, right? And frictionless adiabatic processes are called isentropic. Why is that? Frictionless adiabatic processes. What was isentropic again?
So you can differ.
No change in the entropy. Good. And where's the entropy on the board?
It's not in there. Where the pressure stays the same. No, we can now.
No heat is added, right? Where's heat here? dE. Okay. And a frictionless process, not going to add any heat, right? Going to keep that TDS the same. So P and V are going to have to play with each other. Okay. So you may look at something like this. And let's imagine that this is V, I believe. Let's do P up here. And that's sort of the traditional way of drawing these. And for a constant temperature, for an ideal gas, how do P and V behave? You want to draw it for me? Okay, okay. Yeah. So P and V for a constant temperature, they form a curve on this. Okay, what does that mean? Say it differently. Inverse of
Each other.
inverse of each other. So everyone's keep going. So 1 over R phenomenon, right?
Oh, that's good, yeah.
You're familiar with 1 over R, 1 over X, 1 over V. Okay, good. So that's the temperature. Let's call that T1. Okay. And then let's do another one. And I've drawn this perfectly. Okay. And that's T2. How do I get between them? Let's say I draw an adiabatic. Okay. How would these connect? Something like that. What's this section? Let's say I'm going from 1 to 2. Expansion, and now we can add a little qualifier to that. Isothermal expansion, very good. Okay, now I want to go from 2 to 3. What is it?
Adiabatic.
It's adiabatic. And what was it again? Adiabatic what? Oh, my handwriting looks really good today. I don't know what handwriting I like that. This is a really good piece of chalk that I hope I don't break. Okay, I want to go to 4 now. Now what do I do? Yeah.
So 2 to 3, why would the heat not change?
Yeah, it's a good question. Very good question.
Because it's expanding, it's also.
Right. So recall that when we're moving through this process, we're in local equilibrium. Okay, so the path that we take matters. The final state matters as well, but how quickly we move through the fluid also matters. So for example, if you just rapidly make these changes, they absolutely will not be adiabatic, right? In fact, we're going to get to stability in stratified medium in 2 seconds. But when I say that this is adiabatic, I've baked in an assumption, right? That I'm hoping that you see, okay? That along the way, the properties of the fluid themselves are able to realign themselves such that they take place without the addition of heat, okay? If I drew that line and I didn't tell you it was adiabatic, then you would just say, expansion. Does that make sense? So what's this bottom one now? Very good. And the top one? Good. Okay, what do adiabats look like? No, they look like that. Good. Questions about this? Okay. So what else did I want to say? There's an exercise 113. Maybe I should have given that to you. You guys want to do 113 as an exercise? Or you want me to just show you what the result is? Just show it. I don't fucking want to know. Okay. So interestingly enough, you can write a couple fun things down. Okay. P over rho gamma. And this is equal to constant. Okay, just a constant. Doesn't matter what the constant is because all we care about is the relationship between them. So if, for example, you wanted to say P1, P2, right? You could say P1. Oh my God, this is the worst part of the board. Oh, God. Oh. Okay, so that would be true at all of the locations. And in fact, because we have this nice equation of state, which relates P, rho, R, and T, we can make many other statements as well. For example, we can make this statement. That is this disgusting beast. Is that clear? Doesn't have to be intuitive. Just make sure that my drawings are fine. Okay. And finally, this is the one that people like the most. Oh God. Okay. So when I said, how did you draw that weird line between the things? Well, that's those. And you can connect them along every single location. And none of these have V in them. You have to turn that crank in order to get it back into a world that you like, EV space. But these here describe an adiabatic process going from point 2 to point 3. That is the curve. Does that make sense? You can kind of see it if you think about it in the context of what volume and density mean. Okay. Yes or no? Unhappy? No? No. Okay. I'm going to show you the stability of a stratified fluid, and you tell me if that still doesn't work. Okay. Before we go on to that, let's talk really briefly about sound speed and thermal expansion. So in metal, for example, what does the thermal expansion depend on? Yes, and also mass, yeah, certainly. And Mass and volume all take together. Yeah, that's the same. They're both dependent on that. The same at all temperature? No, it's temperature dependent. It's also temperature dependent for fluids. In fact, in an ideal gas, perfect gas, I should say, sound speed goes like the square root of the temperature. Fuck. Yeah, that's just what it does. I don't know why. And of course, the expansion, the thermal expansion is like 1/T. Okay. Okay. So let's think about a parcel of fluid. Okay. And we're going to put in a gravitational potential. So this is the gravitational potential. The bottom is down here, and this is up. Okay. And we're going to let the pressure, the density, and the temperature vary with height, but we're going to say that it's static. Okay. So it's all fully, no motion. It's all just sitting there. Okay. And we're going to describe something called an isentropic curve. Now you'll notice that's really well drawn. Wow, I'm going to say you're so good at drawing isentropic curves. Okay. Same exact angle. You're like a graphing calculator. So what does this mean here? Okay. Let's imagine a situation where you have a parcel here at location Z, or Z naught, and you raise it up. Okay, you raise it up to this place Z plus eta. And at that new location eta, it'll have some density compared to its surroundings. Okay. If it's more dense than its surroundings, what does it do?
Go down.
Goes down. If it's less dense than its surroundings, goes up. If it's exactly as dense as its surroundings, just stay there. Good. Now you fully understand isentropic curves. Isentropic curves. Okay, so this is the isentropic curve that goes through these 2 points, O and C, starting at the origin and going up to a reference level. If you are more dense than the surrounding gas at this point, you fall back down. If you're less dense, you keep going. Yeah.
For me, where's this different?
What do you mean buoyancy?
Like the pressure that's beneath whatever you're looking at your object, and pushing it back up while gravity's pulling it.
Yeah, there's a balance of pressures here, right? So above, you have all of this column of fluid, and below you have gravity. Right? Gravity wants to pull it down, and it's bumping into all the fluid below it, and it has all the fluid above it as its weight. Right? So if you have some profile and you take it this way, okay, let's say you go from this point to this point. Now here's a hard part. I always fuck this up. Is this steeper or shallower than the adiabatic curve? Raise your hand if you think it's steeper. Raise your hand if you think it's shallower. Raise your hand if you didn't understand the question. Okay, let's say it again. Okay, so I'm going to connect this point here and this point here, similarly to how I connected them there, O and C. Okay, and now I'm going to go from here along this path. Okay, to a different point, not 3. We'll call it 3A. Okay. Is this path steeper or shallower? Steeper. Raise your hand if you think it's steeper. Okay. Raise your hand if you think it's shallower. And not fight. So talk to your neighbor really quickly. Try to convince them of whether it's shallower or steeper. And what does this tell you about the fluid?
Yeah.
So hold on, just quietly talk to someone next to you and try to convince them of your answer if they have a different one. If they don't have a different one, find someone else. And then what does this mean about the fluid itself? I don't know.
You said.
Enough to record my lectures.
Are you gonna really get something?
How did you know that?
Look at the film that you're currently recording.
I mean, I think I am. Let's see what it says. Yeah, it says I'm recording. Okay, so what's the answer? Anyone think shallower? Why do you think shallower? Raise your hand.
Partly because you said you messed it up, so I figured it looks steeper, so.
Okay, just making fun of my artistic challenges. Okay, go ahead.
I said because you're going down in pressure, so it should be shallower.
Yeah, right. So I think that I always fuck it up when I talk about steeper and shallower. I tend to fuck it up because I tend to mix them, but I didn't draw it improperly. So in fact, this is steeper, and I like to think of it in the context of skiing. Okay, which would you be less likely to take your grandmother on? Right? Would you want her to go on this one or this one, 3A or 3?
Do you like her grandma?
You assume that you like your grandma. Okay, so here, of course, this is less steep. This is a shallower curve. So when we talk about this in the context of this isentropic curve, this is set for the medium. Okay, and all curves that connect lower than this are what we call stable. Okay, so if the fluid takes a path from O to here, okay, stable. It's probably gonna go back down. If it goes from here to D, it's headed off, unstable. Okay. And of course, if it goes up to C, we already said. What happens at C? Which direction does it go? Just stays there. It's neutrally buoyant. You raise it exactly along the adiabat, it doesn't have any interest in going anywhere. Right? You bring it up, you just drop it, and it's there. Right? The fluid's neutral. Okay. Makes sense? Yeah.
So if it goes to E, it'll drop back to 0.
Well, not necessarily to 0, but it will drop, right? Because here at some location, this fluid that you brought with you, the C fluid, is now lighter than the B fluid is. It's gonna sink. Right? Because at this location, this is the true value at this location, right? This is the density at that location. You bring this fluid up, and its density is greater. Or sorry, less than the fluid at this location, keeps going. Make sense?
So the fluid is unstable, then it will rise.
Mhm.
Stable, then it will go down.
Yeah, technically neutral is still stable, but yeah. Okay. So let me show you one more thing. Exercise 115. I'm happy to assign if you want that. It wants you to find the displacement zeta when a fluid parcel is moved to a new altitude z. Okay. And let me just write this equation down really quickly. Oh shit. So this is what you end up with. What order is this playing in? Second order what?
Differential.
What? Yeah. What kind of differential? Ordinary. Okay. Ever solved this before? Computational did, yeah. Okay, that doesn't help me. I don't have a computer in front of me. I can never do this. Yes, okay, in fact, we can do this, and we can do this with our brains. Okay, so what is the solution? What does it look like? Yeah, oscillating function. How did you see that? What if I call this n squared? What would that look like? It would look like maybe bx squared bt squared plus n squared x equals 0. Does that look like anything you've seen? Harmonic motion. Now wait a second here. That's interesting. So this thing here, n squared, it's kind of got a jumbled mess inside of it, right? What does this thing mean?
The change in density over the change in height.
Okay, and where did I use that? Change in density over change in height is the word for that. Sure, that was one of them, but it's the, what am I describing when I take a derivative? It's a slope. The slope of the density, right? So this is a slope. And this is a slope. Good. Good. So these are two slopes. And it's the difference between two slopes. And which slopes am I talking about? What's that? Yeah, so you have one here, which would be the one that you're considering, and then whatever your new one is, your DA, row A. Okay? And if they're exactly the same, what is the motion of the parcel fluid? Think about all the solutions here. Fluids have the same slope. I bring this parcel fluid up, and then I let go. It should stay there. And do the equation of the motion say that?
Yeah, because, d squared actually d squared would just be.
Right, because n squared 0 in that context. And then that's a context, right? Okay. All right, what are the other solutions? So it can be 0, it can be positive, and it can be negative. Okay. So if it's positive, you get what kind of oscillation?
I think it's driven, right? Yeah.
There's another one.
That looks like a spring.
Oh, it's like a spring, and that is kind of motion, right? Okay, so if this is positive, then this is positive, and this becomes right. So what? Say louder. Yeah, that's the return. That's a storing motion. Okay. And if it's negative in here. Gotta make that a positive there. Uh-oh. And now dx squared dt squared is proportional to x. What does that do? It's out in a space. Fuck. Okay. Okay. So how do we understand both of these? Well, they can be understood with something like an exponential. You're gonna use a special type of exponential. You're gonna add a little I in there. Right? You take two derivatives of something with an I, you get a negative sign. Ever seen those? Yeah.
Wait, so if the equation equals negative, then it's going up.
So that is a restoring force, right? So I fucked up a little bit of the letter use there, but think about it in terms of zeta. Zeta is displacement from the origin. As I move it up, away from the origin, the restoring force is to go back towards the origin. If I press it down below, the restoring force will go back towards the origin.
Oh, so
Yeah, so when n is positive, you have a stable fluid. When n is negative, you have an unstable fluid. Now, the interesting thing would be is if you take this fluid and you push it down and it's unstable, what happens? It's going to get shot back up and it's going to keep going past the place it started. Does that make sense? So it's like if you had a concave bowl like this, and even though you roll the ball up initially, oh, this is great, it rolls way back down and you never get it again. It's still unstable, just not in the way you typically think about it. Yeah.
So can you repeat the whole like when n is positive and then negative? I didn't know right.
Yeah, it's in your book. Okay. So n here is a fun name. It's the Brunt-Väisälä frequency. And this is everything that I said so far. We got the solutions, you got you have this exponential form that uses sines and cosines when n is positive, and increasing exponential when n is negative. Okay, those are the solutions to the formal equation. And they're one solution if you use a combination of sines and cosines with exponentials. With imaginary numbers. And the thing that I want you to take away from here is that this definition here talks about a difference in the slopes. So for example, how the density changes as a function of distance is a property of the fluid. So if you, let's say you have a little weather balloon and you're bored tomorrow, you got a thermometer on it and a camera. You could let that balloon up every 5 minutes as it goes up. You could take a vertical temperature profile. You could convert that directly to a pressure profile, or you could use it in this form. You could change it slightly. And you would measure the change in temperature as a function of height, a property of the fluid, right? And as long as it was smaller than the adiabatic lapse rate, which is this middle one here, okay, then the fluid is stable. Okay, because any perturbation that occurs is just going to wiggle. You ever seen a wiggle in a fluid on Earth? Yeah, what are they? What's that? What? Yeah. So sorry, I'm talking about like in the atmosphere itself. Have you ever seen like an atmospheric wiggle? What kind of clouds? Big clouds that form. Yeah, there's line clouds. They have like lines like this, 1, 2, 3, across the sky. No, that's an individual line. Multiple lines in a row are evidence of gravity waves. You are looking at a gravity wave perturbation. What's happening? Hot fluid moving up, cooling, and then descending, right? Like this, up and down, right? As opposed to, if it's unstable, just leaves. You see evidence of unstable fluids. It's like anvil clouds, like big thunderous rain clouds, pulling material up into them. Those are unstable, right? Now, does this type of ideal gas treatment, does that work everywhere in the atmosphere? No, because anytime that you went unstable at all, all the fluids suddenly would be sucked out into space. So that doesn't make any sense. But you can look locally, right? Let's say you look in just the 30 kilometers nearest the surface. You can make statements about an ideal gas law. You can make statements about an adiabatic lapse rate. Okay. Fuck, we're not getting through this very fast. Okay. That's fine. That's fine. I'm not freaking out. Where's my thing? I left it over. So this is how it really looks in the atmosphere. Which parts of this are stable? Good, good. Yeah, so this section here. Anywhere else?
Also where it's neutral.
Also where it's neutral, good, and
Where it says very
the
stable.
part where it's very stable. Good. So in fact, look at this. This is the temperature as a function of height, right? And what do we want to see here? We want to see an adiabatic lapse rate that is not steeper than the one that we're prescribed, which is on Earth about 10 centimeter or 10 Celsius per kilometer. I think. Yeah, that's about right. I read that off right. So there's the slope. And what would an unstable layer look like?
More like,
So move my arm.
it'd be more to the, you go up,
But what part of my arm?
your elbow.
My elbow. Like that? Is
Yeah, like that. That'd be unstable.
that unstable?
That's interesting.
Oh shit, hold on. So now here we have this problem. Is shallower better or worse here? Okay, so imagine this line here. This part here, is this shallower or steeper?
That's steep.
Yeah, it's steeper. Because remember that temperature and what I wrote over there, which is volume, are they related? Inversely proportional, right? They're right up there. Right? Okay. All right, so we have to be careful when we think about these types of things, but it's fine. I promise you it's fine. Okay. One thing that we want to describe here is this process in the bottom of an atmosphere. You can solve for these equations. Oh my God, we're out of time. We're just going to leave this up here before we get into kinematics. So we're just one lecture behind. It's fine. And that is the scale height relationship. So this is how quickly the atmosphere is changing as a function of height. And in particular, this E folding length. So if you go up to a place like Colorado, about 5,000 feet up, how much less oxygen can you breathe? How much less atmosphere is up there? And if you treat it like a ideal gas law, which is correct to first assumption, you treat it like it's hydrostatic, correct to first assumption, you get about 80% air. Okay. This relationship we could probably start with, but you're going to solve that at the beginning of Wednesday's class. Okay. So don't forget to read page 25. Questions?
Wait, so for the last slide, which one was the more unstable? Or which way would it be more unstable?
So if you go from here to here and you get a larger temperature difference, right, that would be more unstable. Right, because this is very stable.
What is that?
I don't know if it's bad, but it's different. It's not stable. So this is why I said you have to be careful with the words steeper and shallower always being quote unquote stable or non-stable. And I always fuck these up because you have to really look at what's physically changing here. Yeah.
This is only up to like chapter 2, right? Or
This is chapter 1. We haven't started chapter 3. We're gonna skip chapter 2. It's just math. It's like Stokes' theorem and shit like that you don't need unless you really want it. I would recommend reading it. If you haven't done E&M, you should probably be familiar with things like circulation. We will just talk about it in the context of fluids, which I feel like is more intuitive, because then you'll be like, oh, fluids do that thing, as opposed to arbitrary integrals around a closed curve, which are stupid. Okay. Questions? Yeah.
For the group rating? Or
Yeah.
So are you assigning each of us one?
No, you'll see everyone's work.
Oh.
There are not comments. There will be questions that I ask you. If we want to put comments, you're welcome to. You're welcome to talk about it. You'll see your own work. You know, it's fine. I mean, you're taking pictures of stuff, right? Okay. Other questions? Yeah. So the only thing that I didn't do in chapter 1 is dimensional analysis. You're welcome to do dimensional analysis on your own, but I think in practice, we're just going to learn that from the process of deciding how to approach a problem. There are a lot of problems to deal with dimensional analysis in fluids, like how you set up the equations properly. And then when you get to chapter 3 is much smaller than chapter 1 was. It's just harder because there's tensors, and if you hate math, you're not going to like tensors, but they're just matrices. They're not bad. They just have a bad name. Got a bad rap, you know? Yeah, I mean, read the whole book. But as I was saying to Desiree, right? Like, so I when I'm saying read the whole book, like what I mean by that is like, go through the process of just skimming the material so that when you come into class, you have questions or you've seen it before. And that way, when you're confused on something, right, it's the second time you've seen it. And then you read it again, the parts that you are really interested in, and you'll have a much better understanding, right? So I don't want to like assign reading. I'm going to give you the whole chapter because it's not like there's parts that are shitty in it. I personally, when I read, I don't read the examples. Now, is that a good thing? No, probably not. But later on, maybe if I need to do a homework problem, I'll be like, is there an example that's close to this? I'm like, oh, now I get it, right? Does that make sense? Okay. Not every example, not every exercise is necessary to do. Some of them are, some of them aren't. If you find that I'm going to have a very strong planetary science leaning in this class, that's not surprising, right? That's what I do for a living. But what that means is I'll probably steer some of the topics towards that. If you find, oh, it's in the book, but it wasn't covered but in class, read it. Okay, anyone not giving me homework? Anyone not giving me progress reports? Questions? Yeah.
Really understand anything the whole lecture.
Oh, really?
So that's why I'm asking like what I like really need to like read or like watch in the lecture or something afterwards so I can get what we're doing. Cause I'm honestly super lost. And like this whole lecture, I was